Lowry theory of acids and bases. Bronsted and Lowry, these are the two scientists, belongs to two different countries, simultaneously proposed this theory. That's why it is known as Bronsted and Lowry theory. And this is also known as protonic theory because it explains the behavior of acids and bases in terms of proton. Proton is a fundamental particle of an atom which is present in the nucleus, and it is present deep inside the atom. Outside the nucleus, we will have electrons. Here in hydrogen, we have one proton and one electron. In chemical reactions, nucleus has no role in normal chemical reactions. Then why we calling as proton? Proton is nothing but H plus ion. Proton is nothing but H plus ion. And this H plus ion is not exist in free state. It always associated with H2O molecules. So its formula, it is known as hydronium ion, H3O plus or H9O 4, like that. As a bulky species, it will exist. Generally, we represent it as H3O plus. Now, according to Bronsted, any species which can donate a proton to other species is known as acid, and the species which can accept the proton is considered as a base. For example, if HCl is reacting with H2O, it gives us H3O plus Cl minus. H3O plus Cl minus. Here HCl is converting as Cl minus. H2O will convert it as H3O plus. Conversion of H2O into H3O plus will take place when one proton is added to it. H2O will convert into H3O plus only when H plus ion is added to it. This H2O will convert it as H3O plus when a proton is removed to it. So here in forward reaction, H2O is accepting a proton. So the proton which accepts, the species which accepts the proton is considered as a base. Now here HCl is converted as Cl minus. HCl will convert it as Cl minus only when it loses H plus ion or it donates H plus ion to other species. So in forward reaction, HCl is donating H plus ions to H2O. So HCl is an acid, H2O is a base. In backward reaction, H2O is converting into H2O. H3O plus is converting into H2O. That means it donating a proton. So it is an acid. Cl minus converting into HCl. That means Cl minus is accepting H plus ion to convert HCl. So here it is considered as base. So in the reaction between HCl and H2O, HCl will act as an acid, H2O will act as a base. In backward reaction, H3O is considered as an acid and Cl minus is considering as a base. Now let us take another example. NH3. When reacts with H2O, it gives us NH4 plus OH minus. Carefully observe this reaction. In this reaction, H2O is converting as OH minus. So conversion of H2O into OH minus will take place when H plus ion is removed from it. That means it is donating H plus ion to NH3 so that NH3 will convert it as NH4 plus. So here H2O is donating proton, NH3 is accepting proton. So H2O will behave as an acid, NH3 will behave as a base. In a reverse reaction, that is in the backward reaction, NH4 plus is converting as NH3. That means NH4 plus is donating one proton to OH minus so that OH is converted as H2O. So here NH4 plus is an acid, OH minus is a base. So if we observe these two reactions, H2O in the first reaction will act as a base, in second reaction it is acting as an acid. So those species which can donate a proton and accept a proton, such are said to be amphiteric solvents. Amphiteric. Amphiteric means they can donate a proton as well as accept a proton. They are said to be amphiteric solvents. Here H2O acts as a base in presence of HCl and acts as an acid in presence of NH3. So H2O is considered as amphiteric solvent. Amphibians, biology students are well known to it. Amphibia, they can live both land and water. Such species are said to be amphibians. Amphi means both. So here H2O has both acidic character and a basic character. In presence of HCl, it acts as an acid, but in presence of NH3, it is acting as a base. Sorry, in presence of NH3, it is acting as an acid, and in presence of HCl, it acts as a base. Now, here, HCl is an acid. By removing H plus ion, Cl minus is forming, which is a base. H2O is a base. By accepting proton, it acts as an acid. Similarly, here NH3 is a base. By accepting proton, it will convert it into acid. H2O is an acid. By donating a proton, it will convert it into a base. So here, in all these four acid-base pairs, the difference between acid and base is one proton. From acid, if you remove H plus ion proton, it gives us a base. For a base, if you add proton, you are getting back the original acid. So that acid-base pair, which is differed by one proton and interexchangeable, acid into a base or base into an acid, by exchange of a proton, such acid-base pair is known as conjugate pair of acid and base. Conjugate pair of acid and base. Conjugate pair of acid and base means a pair of acid and base which is differed by one proton and interconvertible by exchange of protons is known as conjugate pair of acids and bases. So from acid, if you remove a proton, you will get its conjugate. For example, let us see some examples. HCl. By removing one proton, you will have Cl minus. So this is acid and this is base. This pair is called as conjugate pair of acid and base. For H2SO4, if you remove one proton, you will get one HSO4. This one HSO4 is a conjugate base of H2SO4. If we remove another H plus, you will get SO4 minus 2. So here, with respect to SO4 minus 2, HSO4 minus is an acid and SO4 minus is a base. That means HSO4 is a base with respect to H2SO4. But same HSO4 is an acid with respect to SO4 minus 2. So the pair which is differed by one proton and interexchangeable base into an acid by adding H plus ion, or acid into a base by removing H plus ion, that pair is said to be conjugate pair. Similarly, H3O plus is an acid with respect to H2O, where H2O is a base. This H2O is an acid with respect to OH minus. So with respect to H2O, OH minus is a base. But this OH minus, and further removal of H plus ion, it converted as O minus 2. So with respect to O minus 2, OH minus is an acid and O minus 2 is a base. Sometimes in the examinations, they will give one species and ask us to write conjugate. So if H2SO4 is given, its conjugate base is HSO4 minus. If HSO4 is given, if they ask us to write conjugate acid, H2SO4 is the conjugate acid. If they ask us to write conjugate base for HSO4 minus, conjugate base is SO4 minus 2. So by removing H plus ion from an acid, you will get conjugate base. By adding H plus ion to that base, you will get conjugate acid. So conjugate pair of acids and bases. Conjugate pair of acids and bases are a pair of acid and base which is differed by one proton, and it can be interchangeable by adding or removal of proton is said to be conjugate pair of acids and bases. Now here we have learned so many definitions. One is acid. According to Bronsted theory, acid is a species which can donate a proton is said to be an acid. Base is a species which accepts a proton. That means proton donor is an acid and proton acceptor is a base. And third one is amphiteric substances. Those species which can donate as well as accept a proton are said to be amphiteric solvents. And in terms of proton, solvents can also be classified. They are, first one is amphiteric solvents. First one is amphiteric solvents. Amphiteric solvents means those substances which can donate a proton as well as accept a proton are known as amphiteric solvents. Another one is protonic solvents. Protonic solvents means those substances we can donate a proton are said to be protonic solvents. Third one is aprotic solvents. Aprotic solvents means they neither donate a proton nor accept a proton. They are said to be aprotic solvent. Then photophilic solvents. Protophilic means those solvents which can absorb protons or which can accept a proton. Philic means affinity, attraction. So those species which can attract a proton are said to be protophilic solvents. So in terms of proton, the solvents or substances can be classified into four types. One is protonic solvents. Those substances which can donate a proton are said to be protonic substances. That means all Bronsted acids are protonic substances. Then second one is protophilic substances. Protophilic means The substances which accept protons are said to be protophilic substances. Then amphiteric substances, those species which can donate a proton as well as accept a proton are said to be amphiteric substances. And aprotic substances, that means they neither donate a proton or accept a proton, are said to be aprotic solvents. Aprotic solvents example, benzene, carbon tetrachloride, methane, or hydrocarbons, etc. Protogenic solvents are protonic solvents or protogenic solvents. They are all acids, HCl, H2SO4, which can donate a proton are said to be protogenic solvents. And protophilic solvents, those species which can accept a proton are said to be protophilic solvents. They are bases which can accept a proton are said to be protophilic. And aprotic means they neither donate a proton nor accept a proton. They are said to be aprotic. For amphiteric, H2O is an example for amphiteric solvents. Next. For any acid-base theory, in addition to explain acid and a base, it is most essential to explain both strengths of acids and bases as well as neutralization. These are also two important characteristics of acids and bases. Now, strength of acids and bases. According to Bronsted theory, those species which can easily donate a proton, which are favorable to donate a proton, are said to be strong acids. Those species which can easily donate a proton, which have tendency to donate protons very easily, have more tendency to donate a proton, are considered as strong acids. So, examples for strong acids: HCl, H2SO4, HNO3, HClO4, etc. are considered as strong acids because they have more tendency and they are readily ionizable to donate a proton. So they are considered as strong acids. Then strong bases, those species which can readily take H plus ions are considered as strong bases. Similarly, weak acids, those species which are not easily donate a proton, are not ionizable, they are considered as weak acids. Weak acids examples: CH3, COOH, H2CO3, HCN, H2S, etc. are considered as weak acids. Here you may have doubts. Here hydrogen number is same. Then how can differentiate? With ionic equilibrium or equilibrium constant values, we can get their strengths. Because if we take, for example, HCl when reacts with H2O, it gives us H3O plus Cl minus. If I write equation for CH3 COOH plus H2O, reversibly gives H3O plus CH3 COO minus. If we observe these two reactions, it seems to be similar. But how you will decide that HCl is a strong acid and CH3COOH is a weak acid? For any reversible reaction, we know that there is an equilibrium constant. So for this equilibrium constant, if you write For first reaction, Kc is equal concentration of H3O plus into concentration of Cl minus by concentration of HCl into concentration of H2O. Here you will have certain value, this ratio. For the second reaction, if you write equilibrium constant, Kc is equal concentration of H3O plus into concentration of CH3COO minus by concentration of CH3COOH plus into concentration of H2O. If we observe these two equations, Kc values, you will have maximum Kc value for this and minimum Kc value for this. The minimum Kc value for this is because here the concentration of these ions are very less when compared to the concentration of these ions. That means here forward reaction is more prominent, whereas here backward reaction is more prominent. Backward reaction more prominent means the CH3COO minus is more affinity to accept proton, and it is instead of as CH3COO minus, it's preferred to be as CH3COOH. It means CH3CO has more tendency to accept a proton. So this is the conjugate base of a weak acid. So conjugate base of a weak acid is strong. So all weak acids conjugate bases are strong bases. So strong base means the species which has more tendency to accept a proton are considered as strong bases. Here these are considering as weak acids because they prefer to be in a molecular state. Their ions are not stable. Their ions have more tendency to accept a proton. That's why they are in molecular state. And hence, the conjugate bases of these acids, CH3COO minus, this is a conjugate base of CH3COOH. Similarly, HCO3 minus is a conjugate base of H2CO3. Cn minus is a conjugate base of HCl. HS minus, it's a conjugate base of H2S. They are strong bases. Similarly, conjugate bases of strong acids are weak bases. So, weak bases, examples for weak bases. Conjugates of HCl, that is Cl minus. Conjugate of H2SO4, that is HSO4 minus. Conjugate of HNO3, that is NO3 minus. Conjugate of HClO4, that is ClO4 minus. Because these ions are more stable and these ions remain as ions. That means they are not accepting protons. Since they have no tendency to accept a protons, they like ions only. They stable in ionic state only. That's why we are considering as weak acid, because they has less tendency to accept a proton. If has more tendency, they might have converted into molecular state. Cl minus by accepting a proton, it can convert it into HCl. HSO4 minus by accepting a proton, it can convert into H2SO4. But it prefers to be in ionic state rather than in molecular state. That's why these ions have less tendency to accept protons, so hence they are considered as weak bases. So for strong acids, conjugates are weak bases. Weak acids, conjugates are strong. So weak acid give strong conjugate base. Strong acid give weak conjugate base. So the conjugate base of a strong acid has less tendency to accept a proton. That's why it is considered as weak base. Neutralization. Neutralization means losing of acidic character by an acid or gaining of or losing of basic character of a base is said to be neutralization. Generally, when an acid reacts with a base, that reaction is considered as neutralization reaction. So, in any acid-base theory, to explain the neutralization process is also an important property. So here, according to Bronsted theory, Neutralization is a process in which a transfer of proton will take place from one species to other. If in any reaction, if proton transfer takes place, such reactions are considered as neutralization reactions. Here there is no condition to formation of a salt and water. According to Arrhenius theory, in Arrhenius theory we discussed that in acid-base reactions, water and salts are forming. So according to Arrhenius, formation of water and salt is essential for a neutralization reaction. But in the present Bronsted theory, there is no such condition. Just a simple transfer of proton from an acid to a base is considered as a neutralization reaction. For example, if you take H2O plus H2O, reversibly gives H3O plus OH minus is considered as a neutralization reaction, because here a proton is transferred from one molecule to other. Or any other reaction, HCl plus H2O will leads to give H3O plus Cl minus. This is also neutralization reaction. So according to Bronsted theory, simple transfer of proton from acid to base is neutralization reaction. Similarly, the reaction between HCl and NH3 will gives us NH4 plus Cl minus. This is also a neutralization reaction. So there is no condition here for the formation of water molecule. In previous Arrhenius theory, we have that condition. In your 10th class, you have studied that theory. But in present scenario, in our syllabus, it was removed. So this is neutralization reaction regarding the Bronsted theory. Now, this Bronsted theory beautifully explains the behavior of so many acids and bases. But the main defect of this theory was it was unable to explain the behavior of acids and bases in which proton transfer is not takes place. For example, if we take calcium oxide, when reacts with carbon dioxide, it will give us calcium carbonate. Calcium oxide is a basic oxide. CO2 is an acidic oxide. Non-metal oxide is acid and base. Metal oxides are basic in nature. These two, this is base. This is acid. So it will give us a salt. This is a just neutralization reaction. But such acid-base reactions cannot be explained by Bronsted theory because proton transfer is not takes place in these reactions. So this theory fails to explain the behavior of acids and bases where there is no chance of transfer of proton from one species to other species. And removing of H plus and releasing of H plus ions is not considered here. So these are the main defect of this is it was unable to explain the acid-base behavior of non-protonic substances.